for many types of vectors in physics, there's often a similar case where you have a vector, whether it's position or velocity or acceleration or momentum or angular momentum, where this vector has a certain direction and this vector is rotating around at an angular frequency omega. And we'll learn about how we can determine the rate of this vector as a function of that vector for these different characteristics. So we'll start out and we'll have the general Cartesian coordinate system, and we're going to define things relative to that. So we have an x and a y, also you could have a z, but this is going to be just simply planar. So we're only worried about things in a one plane, so it'll just be two-dimensional worry about for this. And we'll assume, and this will make these coordinates be inertial. So the x and the y that coordinate system will not be rotating, because any system that has a coordinate system that's rotating, then it's not inertial and Newton's laws don't work on it. This coordinate system could be moving at a constant velocity up or down, but it can't be accelerating and it can't be rotating. So now we have defined our inertial coordinate system, and I'm also going to define a coordinate system that's allowed to then rotate. And so we'll have any vector I'll call r, so we'll start with position, and then we'll see how that extends to many other things. This position vector, so relative to the center of my inertial coordinate system, the distance to that point, that vector we'll call r, and it acts in this direction, and it's an angle theta relative to my x coordinate system, and I'll have in my Cartesian inertial coordinate system, I have the unit vector I in the x direction, the unit vector j in the y direction. This one I'll have unit vector r sub hat in whatever direction r is, and then perpendicular to I'm going to define the unit vector theta hat. And then from just trig, I know that, so just forget about this, we're just going to worry about unit vectors at this point, that r hat can be defined relative to the cosine and sine terms of the I hat and j hat. And just likewise, this perpendicular coordinate system, which is always going to be perpendicular to whatever r is, it can be defined as shown right there. Now I can take my derivatives. The I hat, these I hat and j hat, those are fixed inertial coordinates, so they don't move. They don't move as a function of theta or time. But I can take if I know my calculus, I can know the relationship between the derivatives of sine and cosines and get this. Same thing here. I can take the derivative of that with respect to theta. I get that. And one interesting thing you can see is that the derivative of r hat with respect to theta, you can see that this term is the exact same term as that. So that is that. So I can substitute there. So I don't know the derivative of r hat with respect to theta is theta hat. And then looking at this term, I can see that this derivative is minus r hat. And also, we're going to define the term. We could have that the angular frequency is defined as the change in theta dt. So we got some rotation of omega, little omega, angular frequency going around. And these are just going to be used to help us when we're trying to redefine the derivative of this as a function of time with using these terms. Now, so r hat, the vector r has a length, a magnitude r, and it's always going to be in the r hat direction. So so any vector, whether it be velocity, position, it's going to have this magnitude in this direction. Essentially the definition of a vector. If I take a derivative of this vector r with respect to time, using the product rule, I'll get This may change, the magnitude may change in that direction, so it can go longer, shorter, and the and the unit vector r hat could be changing. And so we can just rewrite this. So we write again here. This is just drop down. I can break this dr hat dt into two terms, which are equivalent. I could say d theta dt and dr hat d theta. So if I just cross those out, you can see that's really the same thing. And here's the power we get by doing that. If we continue here, we can say there's the magnitude of r, and we know d theta dt is omega. And from here, the the derivative of this unit vector r hat is d theta, which is theta hat, which is saying it's whatever's perpendicular to it. So you can see that in the direction which is perpendicular to r hat. So that's in the theta hat direction. Okay, that this is the rate of change of r hat with function of time is just the magnitude of that r hat omega. So either you can think it either in the theta direction or perpendicular to the motion. This is the magnitude of that. So I would have d theta. So I have, if I do the dr dt equals just this, the magnitude of r omega. Draw that very well. So what does that tell us? It says if I have a vector of any type and that vectorial direction is changing because it's rotating, the derivative of that vector with respect to time, which is perpendicular to it, is always that magnitude of that vector times omega in perpendicular to that vector. There's also many times in problems we're going to say that the magnitude of this vector is constant, so it's not getting longer or shorter. And because there's a term, if this r hat is just getting longer or shorter, and there's omega 0, then there's this term that's in the r hat direction. But very often we're going to have cases where this magnitude is 0. The rate of change of this magnitude is 0. So that makes this term go to 0. And so therefore the only change in this vector is this. So I have, for example, if I have position, the derivative of this position with respect to time is velocity, and the velocity perpendicular, the velocity, if this thing has rotating with omega, the velocity is the magnitude of r at that instant in time times the angular frequency. And if it's rotating this direction, then the velocity is in that direction, and it's perpendicular to there. So that's pretty interesting. I mean, you could also do the same thing if we have the velocity term. So if there's similar, you could say there's my velocity term, okay, and it's rotating at an omega, and that velocity, and what's the acceleration? Well, the acceleration. So this is my velocity term. I'll call it v. That dv dt is v omega. Okay, so that'd be my acceleration, and it's in the direction that v is moving. So how is, and so now we looked at displacement, we looked at velocity. You could do the same thing. Derivative acceleration. We can look at other vectors. For example, momentum. So here we'll have a particle. We'll assume a particle here's their center of rotation. This particle is rotating around at omega. It has velocity at this moment in time. Let's make the assumption that the radius is not changing. So there's my p. There's my p at that moment of time. At some other moment of time, and p would be here. At some other moment of time, maybe p would be there. So this p vector is rotating around, just like my r vector was rotating around, or my velocity vector is rotating around. So this p vector is rotating as a function of time, and here I've drawn at that one instant in time. And again, I kind of do with the same kind of nomenclatures here. I got my inertial coordinate system. I define the unit vector p hat to go in the exact same direction, whatever p is. We know that the derivative of momentum is the net force on this particle. And we're going to find out what the rate of change of momentum is with respect to time. Well, that's, again, just like here, that's my product rule. I can put this down. I can break the p hat, so the directionality of the p vector. So there, it's that way it'd be there. At this moment of time, the p hat would be here. So this p hat's rotating. And so I can, just like I did here, I can break that into the two terms. That's fine. Again, I know the d theta dt of this p hat is omega. And just like here, I know that, so here's the theta hat direction. It's perpendicular to p at that moment of time. At this moment of time, here's the theta hat direction, perpendicular to p in the direction that p is going. So again, we have the derivative, the rate of change of p with respect to time. The momentum is just how much p is getting longer or shorter in the p direction. So is the magnitude changing? So that's there. And for vectors, position direction is important. So I can think about things in 9 degrees. I'm in planar, and here in the perpendicular to that the p direction, there's always going to be the rate of change of p here, and this term is there. And you can see just it's the exact same thing. So a vector which is rotating, the magnitude of that vector, which is in a perpendicular direction to it with respect to time, you think about the theta or the perpendicular, is just the magnitude of whatever vector it is. If it's r, it's r. If it's p, times omega. So here's my p vector, and then perpendicular to it is the rate of change of p, which is going to be useful for things like finding out the net force on it. And then p, we know, if it say was gamma mass times velocity, and our problem assume speed, much less the speed of light in a vacuum, so we'll make that like 1. So there's p is mv times omega, and we know v of something circling is r omega, so we could use it in this form. So this is that. An alternative we know is that we can place omega with v over r and get this way, very exact same similar terms. And then again, if the p is constant, then in that direction, if it has not constant magnitude, then it can be turning, but in the direction of p hat, it'd be 0. But kind of the more important thing I would point out is this. Now let's jump to another problem. This time we'll look at, for example, a gyroscope. And we'll assume the gyroscope is spinning around this way. So it's kind of spinning like this, about a central axis. Okay? And it has an I, it has moment of inertia, and because it's spinning with a frequency omega, and this is kind of confusing, we have kind of two things spinning. So we'll talk about the little omega, because we got kind of, L has the angular momentum about the center of mass is the summation of the rotational and translational center of mass, where this term is the I omega. So this term, and since it's spinning this way, it has a angular momentum in this direction. And then we're going to have this gyroscope. It's going to be, as the gyroscope is going to be called precessing around here, and the frequency of that is capital omega. So at moment of time here it's like that, and a little bit later this gyroscope is spun around, well, quite a bit later. I'd say the gyroscope's wrong color. The gyroscope's kind of spun around to here, and it's still spinning, and so now it has its angular momentum is in this direction. And then sometime later it was spinning more and the angular momentum be here. You can see that angular momentum has a rotational speed, angular frequency, and in this case, not to confuse, this one is, well, we'll call it the pressure possession frequency. And this right here, I'll still call it the little one. But you should remember, this is not the frequency of the spinning. So maybe I'll call this omega of its spin, which is different than the turning here. The important thing though is this angular momentum vector is rotating. Just like R was rotating, just like P was rotating. In this case, we know that the net torque about the center of mass is related to the change in angular momentum as a function of time. And I could do the product rule again here, do the exact same substitution I did before, and I get that there's a rate of change of angular momentum, which is perpendicular to that angular momentum in the direction that it's spinning. You can see, so there's my angular momentum, and there's my rate of change of angular momentum as a function of time, which is just whatever the magnitude happens to be at that instant of time times omega. Just like this was, just like this thing. So for any vector, any quantity q, whether it be angular momentum, momentum, velocity, position, if we have the case we're on a plane, and that vector is rotating, so the directionality of this is rotating, and it's rotating at some angular frequency omega, we can find the rate of change of that vector, whatever it is going to be perpendicular to the vector in the direction it's spinning, and its magnitude is whatever the magnitude of that vector is at that moment of time times omega. And that's very, very powerful, because you see how it can be used many, many times, because many, many times we have these rotational systems where things are spinning around. And many, many times we have it where the magnitude of this position of this vector, whatever it is, let's say angular momentum, so if the spin rate of that gyroscope is staying constant, then the magnitude of this is staying constant. If the velocity of this term and the momentum term is constant, then the magnitude of that is constant. If this position here is constant, that length, then these terms all are zero. And it makes it really easy to understand the value of this perpendicular to it. But since vectors are independent to each other, this one and this one, even if it's changing length, we still know the term which is perpendicular to it. And then the term that's parallel to it is just the rate of change of that vector itself. So we can still use all that vector. I mean, that's the power of vectors in that they don't interact. If I have something there and another vector there, but this one can do that one, it doesn't affect that. A slight warning about using this without thinking about it. The vector we're considering has to be rotating. For example, in this problem, if I was to think about angular momentum, and let's say the mass is here, and we said it was good for momentum, but how angular momentum? So here it is, if I have R, and I'm worried about the angular momentum about, say, the center point, angular momentum is R cross P, so R cross P the angular momentum at that moment of time is out of the board. And it's magnitude RP. And then at this moment of time, the mass is here, R is now there, R cross P, angular momentum is again out of the board. Angular momentum is out of the board here, angular momentum is out of the board here. They're both the same magnitude because the velocity is the same. They're not rotating. So you have to consider, is that vectorial quantity I'm worried about, is it rotating? And then that's true. If it's not, well then there is, that doesn't hold true, because there's that problem, there is no change in angular momentum.